101テック始まります。今日のテーマはジェミニを生んだ Google の囲碁 AI です。アルファゴという言葉を覚えている方いらっしゃると思いますが、これ Google の AI 研究組織 DeepMind が開発した囲碁の AI プログラムです。このアルファゴが人間のプロ棋士に歴史的勝利を収めたのがちょうど10年前2016年の3月です。でこのアルファゴがですね、タンパク質の折りたたみ構造を予測する AI アルファフォールドというものへとつながります。でこれはノーベル化学賞を受賞した AI の製品なんですけれども、このタンパク質のですね構造が解明されると、さまざまな新素材や新薬の開発が劇的に加速すると言われています。でそんなディープな研究がですね、皆さんも使うジェミニにどんな風につながったのか、そして AI は今後どこまで進化をするのか、今日はアルファゴの開発に関わった Google ディープマインドのトップ研究者トール・グレーペルさん、そしてアルファフォールドの開発に携わっているプッシュミート・コーリさんの2人に話を聞きます。 Google が2014年に買収したディープマインドは当初からゲームを攻略する AI の研究を進めていました。スコアや勝ち負けといった明確な結果のあるゲーム空間は、強化学習と呼ばれる AI が試行錯誤で学習していくための理想的なテスト環境だったのです。中でも難易度が高かったのが囲碁です。チェスは一つの局面で可能な手が20通り、しかし囲碁は300通りほど。考えられる盤面のパターンは宇宙の原子よりも多いと言われます。ディープマインドはまずインターネット上からダウンロードした10万曲の棋譜を読み込ませ、人間の打ち方を AI に模倣させました。そしてアルファゴの異なるバージョン同士で何百万回も対局させる強化学習を進めました。2016年3月、過去10年で最高と称された伝説の棋士リ・セロル氏との対局に臨みます。韓国ソウルでの対局では、アルファゴが人間なら1万回に1回しか選ばないような常識外れの第37手を打ち、 AI の創造性を見せつけました。結果はアルファゴが4勝1敗、 AI の歴史に大きな金字塔を打ち立てたのです。
I would like to ask you about the reason why AlphaGo was a breakthrough. So it's been 10 years since AlphaGo beat one of the strongest Go players, Lee Sedol. DeepMind has been developing AI that could play games well at that time, and Go was the most complex board game for AI. So why was AlphaGo's win important for DeepMind 10 years ago, and what did it mean for the company and its research?
Yes, AlphaGo was really a milestone for DeepMind at the time. I mean, you have to imagine Go is this thousands of year old game, maybe the most complex board game ever conceived by people, cultivated to a high degree in Japan, of course. And after chess, Western chess had been pretty much solved. There was the famous match of Deep Blue beating the Kasparov. Go was one of those big remaining challenges, a beautiful game, very simple rules, very complex strategies. And the big question for us was, is AI, or was that AI at the time capable of delivering a game player that would beat the strongest human player? And it turned out that it was.
What part of the AlphaGo was a breakthrough for you? What did those wins mean for DeepMind?
Yeah, so the breakthrough in AlphaGo was really the architecture and how the system used existing human data and combined that with the AI's planning ability to play Go at this very high level. So the way I like to understand it is that when a human Go player plays Go, there are really two aspects to their thinking. There's a fast aspect where intuition and the appreciation of beauty, of elegance of the game and judgment comes in. And the second way that Go players think about it is to reason through sequences of moves, really to apply our reasoning capability and to plan ahead how to respond to moves in what we call the game tree. And AlphaGo had this unique architecture that brings together neural networks that mimic humans' ability for that excellent quick judgment with the game tree search, which mimics humans' ability to search through possibility, to search through a large combinatorial search space. And by bringing these two architectural elements together, AlphaGo was able to deliver the excellent high-level play, including, for example, the famous move 37 in game 2, which was widely considered not just to be an excellent move, but an act of creation, a creative feat by the algorithm, which genuinely delivered something new, something surprising, and something very effective. And it's those three criteria that define what creativity is. And this architecture was able to produce that kind of novelty in the game, and therefore not just play within the confines of what humans had so far discovered about the game, but going beyond that.
Mm-hmm. I think AlphaGo put a lot of spotlight on DeepMind, and did it help expand the research? Did it help fund the research more, and did it help expand the company from your perspective?
Yes, I think from a reputational perspective, it was a great step for DeepMind to demonstrate these capabilities. And it really also opened the door for further developments. I mean, if you look at it abstractly, what AlphaGo does is it is capable of finding the best moves within a very complex search space. The game of Go is incredibly complex. There are 10 to the 170 different kind of Go positions. And so finding the right move in any given position is incredibly difficult. There's also roughly 300 possible moves available at every turn. And so demonstrating that we were able to systematically search these large combinatorial search spaces in a smart way by applying the neural network technology to allow us to select promising move candidate and judge incomplete positions, that is a universal recipe that we were able to take forward and into a number of other important questions in the sciences, because a lot of problems in science and engineering are also search problems. An engineer, given a problem, looks for a solution. If you look for a new material, that's about the positioning of the atoms in that new material. And so almost every interesting problem can be formulated as this discovery problem in such a huge search space. And that's why AlphaGo was such an important demonstration that machine learning and AI was now able to conquer this kind of problem.
Mm-hmm. But I think the key technology here is, one of the key technologies here is reinforcement learning, and which basically trains AI by trial and error in unfamiliar environments, context, and giving rewards to the right decision. And so it can go beyond the human intelligence. So how do you think the reinforcement learning can push the boundaries of AI?
Yeah, I think that's a great point. Reinforcement learning is an incredibly important development. I think it's useful to maybe contrast it with the more traditional setup, which is supervised learning, where effectively you take data and you imitate what a human does, in the case of AlphaGo. And now if you do that, then it would be strange to imagine that by just imitation, you could actually go beyond what humans can do. But in reinforcement learning, you have a different learning setup in which the agent interacts with the world. In this case, the Go playing agent interacts with the opponent on the board and learns directly from the feedback that it receives. So it makes a move, and later on it will see the consequences of this move. For example, if it wins or if it loses. and it then can optimize its next moves so as to maximize the probability of winning. And this is also how humans learn. We learn in interaction with the environment, and if things go well, we think, okay, I'll do more of this. And if things don't go well, we'll say we'll do less of this. And that's the kind of learning that reinforcement learning represents. And of course, it is super important for the agent world in which we are living now. Well, AI agents need to learn by interacting with the world. You give them a task, they try to solve it. Maybe they fail and they learn something from that, or they succeed and then they learn from that. And you have this interactive loop with the environment, which is, by the way, also the loop of science, of course. Mm-hmm. Scientists work in a similar way. They posit a hypothesis, they perform an experiment, they get the feedback from nature, and then they can revise their hypothesis. So this is, in a sense, the most general knowledge-generating process we know of. Mm-hmm. It was implemented in AlphaGo, and it is implemented in science.
Mm-hmm. Our audience has a strong interest in Gemini and in frontier models. And how do you describe the research of AlphaGo contributed to the development of Gemini?
Yeah, so I think you can draw a line from AlphaGo to modern large language models or like Gemini. So it goes back to what I explained about these two ways of thinking, the fast thinking and the slow thinking. The early large language models were generating spontaneously answers to a given prompt directly, so to speak. And that is the fast way of working. But more modern models have a reasoning step in between. So they receive the prompt, but instead of immediately giving an answer, they can generate intermediate tokens. Think of it like a scratch board on which the model can take little notes and rearrange things to think through the problem, and only then they give the answer. And that is the equivalent to the slow mode, to the tree search mode in AlphaGo, and gives the model the capacity to think much more deeply about these questions. And then, of course, reinforcement learning is the method by which the model is trained to achieve that reasoning.
Mm-hmm. I think that at DeepMind, you're now working on the understanding what the future might look like in the post-AGI world. So what is AGI going to look like from your perspective, and what is the future going to look like?
Yeah, that's the big question that we're trying to figure out. With AGI, different people have different definitions, but one very practical definition is one where you say that an AGI is a system that can do most of what a typical human can do in the cognitive space. We're not talking about robotics here yet. We're talking about things that you could do, on a laptop in interaction with documents and symbols and so on. And I think we're seeing first traces of what AGI looks like in coding. Computer programmers are now empowered in unprecedented ways in their productivity. They can lay out roughly what they want to program, and then they can work in interaction with these coding agents to achieve their goals. And I think that's the blueprint for the future that we're looking for. Coding is a first domain in which this is possible because it's a verifiable domain. We can train agents to do this very well because they can get a crisp feedback signal if it works or not, if the code does the right thing or not. But from coding, these things will spread out into other aspects of knowledge work and will eventually empower people to solve all kinds of knowledge work related problems using these agents.
Mm-hmm. So what are you seeing beyond coding?
Yeah, I think it really pertains to all aspects of knowledge work. You can think about things people do in spreadsheets, when they design presentations, PowerPoint presentations, when they write documents, but also more creative things, maybe in image generation or videos, things for marketing. All of these things, making music, will empower people in this way. And the individual, I think the power that the individual human will bring is the ability to orchestrate this process, and in particular to give it purpose and taste. That is really going to be the human superpower, that we know where we want to go, we know what we want to produce, we have the good taste to make choices about where to go aesthetically, what looks good, what people will like, and so on. But then we can leave the implementation work to the agents. And in that way, every single knowledge worker and creative will be more empowered.
Mm-hmm. Okay. Thank you. That's great to hear all of that.
Google DeepMind のデミス・ハサビス CEO が2024年にノーベル化学賞を受賞しました。その受賞理由が AI を活用したタンパク質の構造予測技術 AlphaFold の開発です。AlphaGo で鍛えた技術を現実世界の難問解決に応用すべく開発されたのが AlphaFold です。AlphaFold はアミノ酸のつながりからタンパク質の立体構造を正確に推測する AI システムです。タンパク質は生命のすべてをコントロールする命を宿した機械とも呼ばれており、この形が解明できれば、がんの治療薬やアルツハイマー病の治療、さらにプラスチックを破壊・分解する酵素の発見など、医療や環境問題に大きく貢献するといいます。世界中の科学者が半世紀の間解決できなかった問題を AlphaFold は圧倒的な予測精度で解決しました。DeepMind は解析した2億のタンパク質の構造データについて全世界の研究者に無料で公開。サイエンスを AI で進化させる取り組みは DeepMind の中でも注力領域の一つになっています。
I would like to explore how AlphaGo turned into Nobel Prize winning AI, which is AlphaFold. But I want to take a step back a little bit first. You're in charge of AI for science efforts at Google DeepMind. And so why are AI labs like DeepMind working on applying AI to science in the first place?
So that's a very good question. Science has a very important role for AI. And there are two sort of key reasons. One is that science is a great application for AI. So if we think about why are we developing artificial intelligence, what does intelligence allow us to do? It allows us to think about the world. It allows us to uncover more knowledge about the world. And so in that sense, science is a great application for AI, for really pushing the boundaries of human knowledge, coming up with new discoveries in biology, in material science, in weather prediction, in fusion, and so many other domains, right? And helping us to sort of solve some of the biggest challenges that we are facing, from understanding how do you treat diseases to coming up with materials and engineering sort of solutions to challenges like climate change. But there is another sort of role that science plays for AI, which is to really test the ability for modern agents to become better. Science sort of gives you a set of tasks by which you can evaluate modern AI systems, whether they truly have the ability to discover new concepts. We are sort of talking on the anniversary of AlphaGo, and AlphaGo had this amazing move 37, which uncovered new knowledge and sort of came up with a new sort of move for Go. And so can we have the analogs of move 37 in biology, in chemistry, in material science, and so on? So it also is a great evaluation problem for AI systems.
Mm-hmm. So could you explain how AlphaGo turned into AlphaFold and what AlphaFold is in the first place?
So AlphaGo was an agent that was which had this remarkable ability to reason about the space of Go moves, an incredibly large space that we didn't think a computer could reason about efficiently, given its size. So the fact that AlphaGo was able to sort of think about Go, think about the game states, gave us a lot of confidence that it can reason, like these modern machine learning systems can reason about similarly large solution spaces. And one such solution space is the space of protein structure predictions. So a protein is, proteins are building blocks of life. Everything like in life, most of these, the phenomena that we see in biology are caused due to proteins interacting with each other. Our genome sort of encodes, like the human genome encodes 20,000 proteins. They are the building blocks of life. Yet we did not know the structure of these building blocks completely, right? For over many, many years, we have found the structures for a few, but we did not know the structures for all the building blocks that make humans and various other living sort of species. And that's what AlphaFold did. It, given a sequence of amino acids, which constitutes a protein, it was able to go from that sequence to a 3D structure for the protein. And in doing so, giving biologists this amazing insight on how that protein looks and behaves. Now, in terms of what are the similarities, although the models AlphaGo used and AlphaFold used were quite different in terms of their architecture and even in terms of how they are trained. But one thing is sort of similar, is that they are both using an amount of data and learning from that data to come up with novel insights and novel solutions.
Mm-hmm. So how can general people benefit from AlphaFold? How does it make our lives better?
Yeah, so AlphaFold, like protein structure prediction, is what we call a root node problem because it has implications across the board in biology, in sort of in enzymes. So it can be used for developing new drugs. It can be used for developing new vaccines. It can be used for developing enzymes that can deal with things like plastic pollution. It can be used for understanding the mechanisms of various diseases and even uncover what happens at the cellular biology level on how cells operate and so on.
Mm-hmm. I think that DeepMind launched a separate company called Isomorphic Labs, which leverages the technology of AlphaFold to accelerate drug discovery. So, and I heard the lab's executive said every disease is on the table. So, tell me a bit about how AI can automate the process and discover new drugs. And are we seeing a drug that can cure all diseases?
If we understand the mechanism of diseases, then we have a way to tackle that disease. And that's what these modern AI systems for biology enable us to do. By predicting the structure of the proteins that interact to make a disease happen, we now have a better understanding of what are the disease pathways. Now, if you have that understanding of those disease pathways, and you have an understanding of what those proteins look like, that gives you information as to what kind of drugs you can create that will influence those pathways. That, for example, if you know that this particular protein is involved in a particular disease, now you can build a small molecule or another protein that binds to that protein to inhibit its activity or, and in doing so, disrupt the disease process or influence the disease process. And so in some sense, like many of the diseases that we are seeing today. Some of them are simple, some of them are more complex. But one thing is clear, that AI gives us more information and better understanding of these diseases. And by doing so, we can now develop treatments to tackle these diseases. This is, of course, a long-term process, right? The process of designing a new drug, for example, takes a lot of time. Not only do you have to find a small molecule that binds to a particular protein or a biologic that interacts with the protein, but then you also have to think about its toxicity, what is its dosage, how would you synthesize it, what is its effect in terms of clinical trials, and so on. So it's a long sort of process, but we are making rapid progress towards the use of these systems for treating diseases.
I can imagine AI can work and do research 24/7, 365 days. So how is AI doing research by itself going to look like for you?
Yeah, so I think, AI systems definitely have that advantage that unlike the human mind, which is a remarkable sort of entity, it can reason about so many different things, but it needs to sleep. The artificial sort of mind, it can continue to sort of operate. You can easily sort of replicate it and run it multiple times. And in fact, that's what we are seeing. Modern AI agents, so our agents like Co-Scientist or AlphaEvolve, they are able to search over very, very large spaces and do very deep research, because they can they are not limited by the limits of the human mind, right? In terms of our speed or the breadth of what we can understand. But at the same time, there are certain things that are fundamental limitations. So similar to what happened in the AlphaGo matches against Lee Sedol, there are brilliant moments like Move 37, which, by the way, when it was first played by AlphaGo, most of the commentators thought that it was a mistake. Only later, people realized that it was an ingenious move. Now this is the same sort of challenge that we have in science, that these modern AI models can come up with amazing insights, but they can also come up with hallucinations. So how do you distinguish between hallucinations and amazing insights? So that is the type of research that we are now working on to ensure that modern scientists are able to use these tools effectively to accelerate research.
Mm-hmm. OpenAI, some outlets said they expect their AI models to work like AI research interns by 2026 or fully autonomous AI researcher by 2028. Were there any goals like this at Google DeepMind?
Our goal at DeepMind has always to push the boundaries of science. So for us, the most important thing is to develop AI systems that can help humans in accomplishing different tasks, whether it's scientists, whether it's engineers, whether it's programmers. We want to develop models which can really sort of help transform how something is done, not bring about an incremental improvement, but a transformative improvement in how a particular task is done. Now, in terms of what is the role that AI systems are going to play in the scientific workflow, you can think about scientists today. They think about what they need to solve, but also how they need to solve it. Modern AI systems can really accelerate the how part. If you give them a challenge, then they can really think about a very large set of solutions and find the solution in an accelerated time. Right? So we will be able to really accelerate the whole scientific process through the use of these agents.
Do you think AI can make discoveries that can win Nobel Prize?
Yeah, I think absolutely. I think AI can help make discoveries that will be Nobel Prize worthy. But I think the interesting question is, what do we ask AIs to solve? Right? In science, a big element of science is to ask the right question and to think about what is the right important problem to tackle, which will have a transformative impact on science. So I think scientists will still have that sort of role to play, but AI systems will definitely be assistants and will be part of the process that achieve Nobel level discoveries.
Okay, great. Thanks for your time. Thank you for coming on the show today. I
Thank you.
appreciate it.
It's a pleasure.
Yeah, thank you very much.